properties of Boolean algebra. I think that was the last part that we talked about. We said with the AND operator we have identity property, which is A, and 1 is A. Identity property of OR operator is 0, A, or 0 will be A. And as you can see with the commutativity, A and B, we can replace them, switch their position for AND operation and OR operation. Both of them you can use that. And associativity, you can add C in the parentheses next to B, and you can take A outside of the parentheses. And for OR operator, you can also use the same property. And for distributivity, you already know that you can multiply A and B or A and C. That's how you can write it. But we said this second one with the OR operator, it doesn't make sense if you are thinking arithmetic addition and multiplication. It doesn't work with that. So what you need to do is you have to think about the logic. Logic is we don't have continuous numbers. We have 1 or 0, true or false, high and low. So if you work with those variables, then you will see that this is true. This expression will be true. And the absorption, for example, this one, if you are thinking arithmetic, then you will see that this is a squared plus AB. But where is AB? Okay, we can say that A and A, which is A squared, can be A, but why A plus or A and B disappeared? A times B. Why is it not there? So that's not gonna work with arithmetic addition and multiplication. But if you think that this A can be 0 or 1, then you will see that this expression is true. So in class lecture, we already proved those things. What we did is we put 1, like let's say A is 1, and 1 or B. So if inside this parenthesis we have 1 or B, what is that? It will be 1 because it's OR operator, and if one of them is 1, if one variable is 1, that means this inside this parenthesis is 1. So A and 1 will be A. Same here. Let's say let's say A is 0 in this one. A is 0, and whatever we have in this parenthesis will be 0, which is A. We already said that A is 0, so it will be equal to A. Same here. If you give 1 to A, 1 plus anything will be 1, so it will be A. If you say that A is 0, 0 plus 0 or 0 times anything will be 0, 0 or 0 will be 0, which is equal to A. So after that, okay, then we have extended logical functions also. How we can have them? This is with the Boolean expression. For the Boolean expression, we can have extended logical function by using not. So not at AND will be NAND, and knotted OR will be NOR. So these functions are computed by complementing the result of the core operation. What is complementing? We know complement numbers from the number system. What did we do there? We had a binary number, for example, 1, 0, 1. If we want ones complement of this number, it was 0, 1, 0. So we are just switching the numbers from 1 to 0, 0 to 1. So, but the two's complement was different. Two's complement, we had to add 1, like whatever the complement of a number is, we add 1 to that one to find the binary two's complement for binary number. So we can complement a variable or the operator, then we will have NAND and NOR operators. So let's look at those now. So we already know those two. We have AND and OR. A and B, which is the output, will be, what was the output of this? Can anybody guess it? Do you remember? What is the output of AND operator? We have these two, A and B is
0.
0. This one?
Again 0, and third one is 0, and
one
only the fourth one is 1.
So what about A or B?
First one is 0, I think, and the other ones are 1.
1, 1, 1.
Yes,
that's correct. So that's what we know already. So if we want to have this one, so we are getting complement of A and B and complement of A or B. It's here. So what we expect is, I was going to ask that, but we just get the complement of this output. 0 will be 1, 0 will be 1, 0 will be 1 in the output, and 1 will be 0. And if we go OR and NOR, 0 will be 1, 1 will be 0, 1, 0, 1, 0. So we just get the complement of the outputs. Complement of this AND output will be NAND output. Complement of OR output will be NOR output. So we can show it like this. NAND versus AND. So NAND is just AND. It's like AND, but its output is complemented. I already said that. A and B complement. So complement of A and B. We can see that output, we have complement outputs. See? Like one's complement of this will be here. 0, 1, 0, 1, 0, 1, 1, 0. And so all the 0 becomes 1s and 1 becomes 0. So it's also, we can clearly see that OR also resembles NAND or NAND, but how? It's upside down. Do you see the output? 1, 1, 1, 0. So for the OR operator, 0, 1, 1, 1. It's upside down. This one is upside down of this. So switch, the bottom one went to up and the top one went down here. So so the table, we just flips and it matched NAND. So if we flip this table, we will have the same A and B. Complement of A and B will be equal to A or B if we flip the table. Okay, so we also have this De Morgan's square from De Morgan's theorem. As I said, so we can transform into any other logical function using this square, like AND and NAND. We have complement outputs. What is complement outputs? Their output is complemented. So 0, 1, 0, 1, 0, 1, 1, 0 between AND and NAND. So between NOR and OR, what do we have? Again, we have complement outputs. 1, 0, 0, 1, 0, 1, 0, 1. If we think about that vertical transformation, we have complement inputs this time. How can we understand that? So, as we said that the output of A and B, output of AND operation, is the upside down of output of NOR operation. See, upside down here. And 1 is at the bottom, 0 is here, 0 is here, this 0 is here. Same here for between NAND and OR. 0 down there, 1 here, this one is here, and this one is here. So what can we do is it in the second page or here? So here, let's talk about it here. So complement inputs, complement output, we understand. We just get the complement of this and it is here. So what about complement input now? So we have, let's start with the 1. So we have 1, 1 input for the AND operation. 1, 1. What is the output? Output is 1. So if we get the complement of inputs, what is the complement of these inputs? We have 1, 1. If we get the complement of the input, what are we going to have there? Just the complement of the inputs. What are they? Do you have any guess? Any answer?
0, 0.
Yes, 0, 0. So if we have 1, 1, the complement of 1, 1 will be 0, 0. So 1, 1 here is 1. What about 0, 0 now? 0, 0 is 1. See, we get the complement of these inputs, and we see that NOR operation have that as output here for the 0, 0. So if we go to 1, 0, 1, 0, complement of 1, 0, what is it?
0, 1.
0, 1. So 1, 0 output for 1, 0 inputs is 0. So 0, 1 is the complement of 1, 0. Go to 0, 1, and you see that output is equal to 1, 0 here. So 0, 1 will be 1, 0. Complement of 0, 1 will be 1, 0. Go to 1, 0, and this is 0, and it was 0 here. Correct. So 0, 0, complement of 0, 0 will be 1, 1, and the output is 0. Go to 1, 1, and output is 0. And same here, if you want to transform between these up and down tables, 0, 0 is 1. Complement of 0, 0 will be 1, 1. Go to 1, 1, 1, 1, and output is 1 equal to this one. 0, 1, 1. We are looking for 1, 0 now for the complement of this. 1, 0 is 1. Correct. And 1, 0 complement will be 0, 1, and the output 1, 0, 1, 1. Correct. 1, 1 will be 0, 0. Complement of 1, 1 will be 0, 0, 0, 0, Are they equal? Yes. Outputs are 0. So that's what complement inputs and complement outputs. Okay. So we have more. We had postulate, and now we have theorem. So the notation is simplified by omitting the binary operator whenever doing so does not lead to confusion. So let's say we are trying to omit that operator, for example. What do we have here? X or 0. Why do we need the gate here? We need a gate for this operator. We need an operation for this. So we can simplify it and say this is X. We don't need X or 0. So that's postulate, which is we assume that this is correct and we know that it is correct. Like it's kind of assumption, you can think. And X and 1. Why do we need this operator here? We can simplify it and we can write it X. And postulate 5 is X or X prime here, which is complement of X. So what is that? That's 1. Why? Because if one of them is 1, the complement will be 0. 1 and 0, or 0 and 1. I mean 0 or 1. And with the OR operation, what do we have? One of them is enough to be enough to have one output. So it's 1. But for AND X and X prime, because one of them will be 0 at least, the output will be 0 in any case. So in any state of X. And we have another postulate here. We can switch their positions. We already saw them. And this one also here, postulate. So distribute them XY and XZ, XY and XZ. Okay, so now let's go to this one. What was it? XY, X, so X or Y, X or Z here. We can see it. So now we also have theorems. Theorems is X or X will be X, X and X will be X, and another one is X or 1 will be 1, because 1 is, if we have 1 in one side of OR operator, anything we have here will be, result will be 1, and X and 0 will be 0, and complement of a number's complement will be number itself. And postulate with that theorem here, we already know this, I showed you. We can put this one in parentheses and take the other one outside. And we have De Morgan theorem here. De Morgan is complement of X or Y will be complement of the first variable and complement of second variable here, and complement of the dual of the operator. Dual of the operator will be AND, or will be AND X prime and Y prime. For AND operator, it's same, X and Y. Complement of X and Y will be X complement or Y complement. And absorption, we already know this one also. We said this is X and this is X. Now let's, so for the postulates, we don't need, because they're basic axioms of the algebraic structure, and we don't need proof for them. But theorems, we have to prove them from the postulates. Let's see how we can prove them. So we have the table here. and we have now x or x, which is x. What we are doing is we can multiply, we can put this in AND operation with 1. And 1, we can write it in this way. How? We are using postulate. First, we are using postulate 2b. Go to postulate 2b, x and 1 is x. So x or x and 1 is still this. Okay. And we use 5a. Go to postulate 5a, x or x prime is 1. You use it here, so we convert 1 into this one from 5a. And now we are going to use 4b. Go to 4b, postulate 4b. So this expression can be written in this form. And let's write this one in this form. What is it? X, or we can call this y here, and we can call the second one z. If this is y, this is z. X or y, x or z. So that means x or yz, x or y and z. So what is that from postulate 5b or 4b? Yeah, 5b. We use 5b, x and x prime is 0. So this part will be 0. X or 0 from 2a, x or 0 from 2a will be x. So we prove that this is correct. What was that? That was theorem 1a, this one. So we prove it. Let's prove 1b now. Theorem 1b. Theorem 1b. X and x is x. Normally in class lecture, I was asking students to do it on board. Now I will show it. What is the time? Do we have enough time? Yes, we have more than enough time. So let's go to that one. X and x will be x. So x and x will be x. Let's prove it. We put or 0 from 2a. Go to 2a, x or 0 is x. So if we call this one x or 0, still same as this one. And that's from postulate 2a. Now we are using postulate 5b. 5b is x and x prime is 0. So this 0 we convert it into x and x prime. So it didn't change anything. And when we have this, we are using 4a now. Postulate 4a. So our expression is in this form, xy or xz. And what we need to do is we need to take x outside and in the parentheses y or z. So get the x outside, x parentheses, x or x prime. What is x and x or x prime? From 5a, it is 1. So we can write 1 instead of this. X and 1 from 2b again. 2b, x and 1 will be x. So this is x. Okay. Now let's go to 2a. The table. What was theorem 2a? x or 1 equals 1. So what we are doing, we are using postulate 2b again. 2b, x and 1 is x. So this is x and 1 is still same, didn't change anything. Now use 5a, 5a. Instead of 1, we write this in this form, x or x prime, which is still 1. And now we will use 4b, 4b. So when we have in this form, we can write it in this form. So what is y? Our y is this, and our z is this. So x or yz. Y comes from x prime, z comes from 1, and that's from 2b. We will have x prime from 2b. And x or x prime, which is coming from here, is 1. So that's how we can prove theorem 2a, which is x or 1 is 1. Now let's go to 6a. 6a is the absorption. Absorption is the so we have this. We are using postulate 2b. Postulate 2b, x and 1 equals x. So we are using it here, x and 1, didn't change anything. And we get it in the x parentheses here, 1 or y from 4a. And yeah, we can, so we don't really need to do this, but we can. And so y or 1, what is this? Is 1 from 2a. Go to 2a. I mean from 3a. Postulate 3a. 3a. Now this is, we change position, and from 2a, x or 0 is x. Is it wrong? Something wrong. Anyways, this is 1, and x and 1 will be from here, from 2b, will be x. And absorption, sometimes we can use the truth tables to prove the Boolean algebra, the theorems of the Boolean algebra. And what do we need? We need both sides of the relation are checked to see whether they yield identical results. So they have to be the same results for the both sides of the equation. So what did we say for this? X, parentheses x and x or y. We said that this is x. From the table, so De Morgan's absorption theorem, x or x and y is x. So we are going to prove that. When we prove it, we will show that x, the output of x in the truth table, will be equal to output of this left side of the equation. So it's here. So we have x 0 0 1 1, y 0 1 0 1. So if you want to write these things in order, so in the exam, if I ask you, you have to write them in this form. So it starts from 0, 1, 2, and 3. So if we have 8 rows, it will go 3, 4, 5, 6, 7. That's how you will write it. To write it in this correct form, that's the way. Start with the second one, 0, 1, 0, 1, 0, 1, wherever you want to go. And when you go to the second column here, 0, 0, 1, 1, 0, 0, 1, 1. If you have another one, if you have the third variable, then you will go 4 zeros and 4 ones, and that will help you to write the numbers in order. If you mix them, it will be difficult for you and it's not gonna be correct. So we wrote them like this. And what is x, y? X and y is an AND operation. So we want at least one of the inputs true. So at least, I mean, not at this one, both of the all inputs has to be one for AND operation. So where is that? This one satisfy our rule here. Both of them is 1, 1, 1 is 1. All the other cases, we cannot have all inputs are true. So we put 0 for them. Now let's go to this one. We are gonna use x and y and x from here to have this one, which is this one. Because we are gonna prove this one equal this one or this one equal this one, they are the same. So x or x and y, x or x and y. With the OR operation, we need at least one of the variable, one of the inputs true. So where is it? 0, 0, 0, 0, 0, 0, 1, 0, at least one of them is true. So 1, 1, 1, at least one of them is true. It's 1. So we had this. So now we said that this and this, they are same, you already know. This one equals x. So the truth table should show it. 0, 0, 1, 1, 0, 0, 1, 1. That means they are equal. So this expression is true. You can prove all the tables like that. So De Morgan theorem. For the De Morgan theorem, what we have, x or y, complement of x or y equals x complement x bar and y bar. Or we can write it in this form with the prime, x or y prime equals x prime and y prime. So what we are doing here is we are getting the complement of the variable and dual of the operator. If it is OR, it goes to AND. If it is AND, it goes to OR. So now let's show it with the table. Can anybody guess how we can write this? Okay, I think if I open it, it will be all open. Yes, anyways, let me show. Do we have enough time? Yes, I have enough time. I need to finish those. So we have x and y. As I said, we are writing it in this one, 0, 1, 0, 1. And the second one, 0, 0, 1, 1. So they are in order, 0, 1, 2, and 3. Now, let's go find x or y. X or y is at least one of them is true. And we can see that they are here. So 0, 1, 1, 1, because none of them is true here. If we want to get the complement of x or y, we just get the complement of this output, 0 to 1, 1 to 0, 1 to 0, 1 to 0. So we convert it to this in this form. So now what we want is, we want to prove that complement of x or y equals to complement of x and complement of y. So let's find complement of x first. What is complement of x? We just need complement of these numbers here, these variables. 0 will be 1, 0 will be 1, 1 and 1 will be 0, 1, 1, 0, 0. Let's get the y complement. The complement of y is 0, 1, 0, 1 will be 1, 0, 1, 0. So 1, 0, 1, 0. But we need to put them in OR operation here. With the OR, I mean AND, not OR. We need to put them in AND operator. So x prime and y prime, 1, 1 is 1. Both of them true. 1, 0, both of them are not true. So 0, 0, 0. So now to prove this, De Morgan's theorem, we have to show that this one equals this one. So where is this one? This left side of the equation. It's here. Where is right side of the equation? It's here. So 1, 0, 0, 0, 1, 0, 0, 0. So they are equal. So that's how we prove it. Now Boolean function. For the Boolean function, Boolean algebra is an algebra that deals with binary variables and logic operations. We already said that. And we are using constant 0 and 1 and the logic operation symbols. What are they? And, or, not. We are using those symbols, and we are using, plus and dot operator and 0 and 1s. For example, this f1 function. This function has this x or y prime and z. That's what we have. So this function will be 1. In which case? In this case. If x is 1. So if this x is 1, whatever we have here doesn't matter. We will have output of 1 because 1 or anything will be 1. If x is equal to 1, or let's say x is 0, then we need 1 from this side of the OR operator. So that means we need to have both of them 1, to have 1 here and 1 in the f function. So to have 1 here, that means y prime and z will be 1. So f1 will be 0 in any other case. If we don't have those, then we will have f1 0. So can we write f1 here? Can anybody say what is f1 here in this case? Is it difficult? If it is difficult, tell me so I will continue.
It's not difficult, but it will take a bit time for me to find the results.
It's actually very simple. You don't have to write all the numbers there and find. You can just
how can we do it?
So, for example, tell me the first 2 or first 3 at least.
Okay, if we need XOR for y prime and z, one of them should be 1 to get 1. Here for first 3 1, we don't have a 1 for x. So if y prime and z is equal to 1, we will get 1, right?
Yes.
Okay. Y prime is 1 here, and that is 0. 1 and 0 is 0. So first one is 0, I think.
First one is 0. So let me tell you like this way. We are looking for x when x is 1, right? Can you see where x is 1 here? This 4, we have x 1.
Is 1 here.
So that means it's satisfied this. So if it is 1, we don't look at this side.
Yes.
That one is 1. So we can put 1, 1, 1, 1, 1. And if it is 0, then we need y prime and z. Y prime and z
should be 1.
1, 1, 1. So that means where is y prime and z in this form? So z will be 1, 1, and y prime will be 1, which is here, right?
Yes.
So this one is 1, 0, 0, and all of those will be 1. I will explain this one again. So here, the complement operation dictates that when y prime is 1, so we said that y prime will be 1 here. That means y is 0. So we are looking for y is 0, z is 1. So y is 0, z is 1 here. And it is 1. Then we don't need to look at the x. 0, 1, 1. Do you see any 0, 1, 1? 0, 1, 1. But we already have 1 from here. So 1, 1. We already put 1 here. So that's how simple it is. And that's the, if you want to write it with the logic gates, we are trying to write this operation. So we call this AND gate, and this is OR gate, and this is NOT gate. So y, if it passes through this, it will be y prime here, and z comes from here, y prime z, and this is AND operator, and here y primes and z, which is this term, and it goes here, and this will be the plus sign for us, x or y prime z, and the first term comes from here, and we combine them here. That's, I didn't start logic gates yet, but I'm trying to show you with the simple ones. Let's go to another function here. I will show more stuff here. So Boolean function f2 this time. We have 3 terms here. This function is equal to 1, in which case this part will be 1, or this part will be 1, or this part will be 1, right? If one of them is 1, it's enough to say that f2 is equal to 1. So to have 1 here, x prime should be 1, y prime should be 1, and z should be 1. That means x should be 0, y should be 0, z should be 1. Why? If you put this one here, you will see that you will get the complement of x and y, and they will be 1, 1. They will be 1, 1, and 1, it will be 1 here. And if you look at here, we have x prime 1, y, and z 1. So if x prime, we are looking for x prime to be 1, that means x has to be 0. So 0, 1, 1. Or we want 1 here. How is it possible? X has to be 1 or y prime has to be 1. If y prime is 1, that means y is 0. So we are looking for 1, 0. So in this 3 case, we will have 1 regardless. So, and otherwise it will be 0. And this set of conditions produce 4 ones and 4 zeros for F2. And we will see it in the table now. It is possible, we can simplify also this. We can use the sum of the identities of Boolean algebra and simplify this. I will show it too. So let's find those in the table. So we are looking for x, y, z, 0, 0, 1. 0, 0, 1. And it's here. And 0, 1, 1. 0, 1, 1. And we are looking for 1 and 0, x, y, 1 and 0, and we don't mind what z is, 1, 0. So y is, x, y is 1, 0, 1, 0. So in these 2 cases, also we can have 1. In this case, we can have 1, and in this case, we can have 1. Let's see if it is correct. Yes. That's how you can examine the function and find the corresponding values in the table. And now this is the logic gate design, logic gate circuit for this expression. So we have and, see, and, actually, yes, and operations here, 3 of them, and we have or, we sum them up. So what we are doing now is x comes from here, this side of it, x, and if you pass this part, it will be x prime. So x prime goes here to AND operation. What else comes here? Y prime, y, after here, y prime comes here, and what else? Z comes here. So x prime, y prime, z in AND operator, which is this first term. And it goes to OR operator here. So it will be plus. There are 2 more terms coming. So let's find the other terms. So in the second case, x prime comes here, and we need y comes from before the NOT gate, comes here, y, and we need z directly comes here, and we have x prime, y, and z, and it goes here, plus, and it's here. So now we have x and y prime in this one. See, this one comes from x, and we have y prime also. Y prime comes from here, y prime, and goes down here and goes plus, we have this. So what we can do here is we can simplify it in this form. So we want the same, we wanted to do the same task with the simple and smaller circuit. So how can we make in this form? from here. So these two circuits are doing exactly the same thing. So if we can have that small one, why do we need to use more component, more material, and make it bigger, and it will cost more? We have to simplify it to make it cheaper and smaller. That's what we need in our world. When you buy a phone or a computer, that's what you are trying to do. You are trying to make it get the smaller one, lighter one, and cheaper one, and faster one. So that's how you are doing it. So what we did here, x prime and z, x prime and z, x prime and z, it's common here, and you get the parentheses, and y prime or y comes from here. So what is that? This is 1. So we had x prime z or x and y prime. So we made it simple. So now it comes here x and y prime, which is the second term, and it goes to OR gate, and from here we have x prime and z, which is the second term here, and we add them into, we sent them to the OR gate, and we had this one. That's what we are trying to do. And algebraic manipulation, I'm gonna try everything. So we are trying to go from this one to this one. So each term here in the Boolean expression, you can see the expression, requires a gate, and each variable within the term is the input. So each term requires a gate, and each variable, so each of those letters will be the input. And a literal is the single variable here. X, Y, Z, these are all literal. And it can be in complemented or uncomplemented form, which is here x prime is the complemented form, and we have x, which is uncomplemented, the original form of the literal. And f2 function has 3 terms here, 1, 2, and 3, and 8 literals, 1, 2, 3, 4, 5, 6, 7, 8. And simplified version has 2 terms, 1 and 2. And we have 4 literals now, 1, 2, 3, 4. So by reducing the number of terms from 3 to 2 and the number of literals from 8 to 4, both in the Boolean expression, we are using Boolean expression, so we can obtain a simpler circuit by that way, as I said. And reducing an expression for the purpose of obtaining a simpler circuit. That's why we are trying to reduce the expression, so we can have a simpler circuit, a smaller circuit, and we will use less material, less component for our circuit, for our computer. When you are designing your computer, you want less material to build it. You don't want like 10 kilograms of a laptop. You want 1 kilograms of a good laptop. Like if you want to buy a good one, of course there are lighter ones, but you want a good one. So we can reduce the simplify this expression by using a map method. We will see it later, not now. But with that method, we can go up to 5 variables. So if we have more than that, like as you can see in our when we were talking about the integrated circuits, which consist of switches and wires and these logic gates inside. They have millions of logic gates in it. So we need to use a computer minimization program. So that means like computer. So let's say computer helps to create another computer by simplifying. Like we are using computers to have another computer, to have optimum computer, like the better computer. We are trying to minimize the expression, the circuits, to create another computer. That's how they help us. And slowly that means the computer helps to produce themselves, like they start producing by, not by itself, but helping itself, we can say. What's that? Let's go. So let's go to this example here. Do we have time? Yes, we have. We want to simplify the Boolean function to a minimum number of literals. X and in parentheses x prime or y. So what is that? What is the result of that? Do you have any guess? What is the simple, like simplified version of this? Anybody have guess? If not, I'll continue. Okay, let's go. Comes here. X and x prime comes from here, and or x and y. So this part will be 0 because at least one of them will be 0 and 0, and in the result we have x and y. What about this one? Any guess? No guess? X or x prime, x or y. Why? Because we had a from the table that I already showed you, we can call this x or y and z, and we can write it in this form, x or y, x or z, in that form. So it goes from here to here. So this part will be 1 anyway, because at least one of them will be 1, and it is enough for our operations to be 1. So 1 and this expression, we have x or y. So what about this one? Any guess? No guess? No guess? So let's go to this one. We can write it in this form this time. We put an AND operation here, and x or x prime. This is 1. It doesn't change anything. And when you multiply it, x, y, z, and or x prime, y, z. After that, you take it to the parentheses, x, y parentheses. 1 comes from here, and z comes from here. 1 or z. And x prime z parentheses here. 1 comes from here, and y comes from here. And this one will be 1. This one will be 1. xy or x prime z. That's the simple version of this. So we got rid of this part. So we have smaller circuit now. We also have complement of a function. So f, we can have f prime, a complement of f, a function f. So obtained from interchange of zeros for ones and ones for zeros. So we are just switching the zeros to ones, ones to zeros. That's how we find complement. And what else? So the complement of a function may be derived from De Morgan's theorem. De Morgan's theorem was here. X or y, complement of x or y would be x prime and y prime, and complement of x and y will be x prime or y prime. And De Morgan's theorem can be also extended to 3 or more variables. So if we have 3 variables, it's here. We have A or B or C. If we want to get the complement of this, A or let's say B or C is X. So we are acting like it's only 2 variables. So we had A prime, X prime. So now let's replace the X with B or C. Now it's again 2 variables here, B prime and C prime, and we can just combine them like this and write them like this. So with the 3 variable we have this, and the theorems can be generalized, and we can have also more variables here, A, B, C, D. We can go up to whatever you want, and we just complement the numbers here, I mean the variables here, and we get the dual of the operators. If it is OR, we make them AND. And here we get the complement of numbers, and we get the, instead of AND, we have OR now for each variable. And let's go to an example.